In our previous video, we discussed conceptualizing statistical control as mathematically holding constant or removing the effect of other variables. In this video, we'll examine one way of thinking about how multiple regression accomplishes this by looking at residuals in our regression model. To do that, let's start by revisiting our example in which we predicted grades based on school quality and study hours. Our coefficients table provides the equation, our regression equation, that we use to predict scores on the outcome based on a participant's values on the predictor variables. For example, if a student attended a school with a quality score of 9 and they studied 12 hours per week, their predicted GPA would be 1.040 plus 0.066 times 9 plus 0.057 times 12, or 2.318. That's a tough school, but remember, this is made-up data. Now, we can plug in any values for school quality or study hours, do the math, and the result is our predicted score for the outcome, grades. That's why we have the y hat with the little hat symbol on top. Y hat is our predicted score for the outcome, y. But in reality, remember, our predictions won't be exactly correct. The true score, the true y, will be different. Maybe higher, maybe lower, but different. The difference is our residual or error. We can see the residual if we write a second equation for our true or observed score and compare it to the regression equation. So here we have both the regression equation for our predicted score, y hat, and the actual observed score where we've added the residual or error at the end. Again, remember, that's the difference between what was actually observed, y, and what our model predicted, y hat. Now, we can write an equation for that residual or error as E sub I equals yi minus y hat sub I, which is just a way of saying that a person's residual or error, E sub I, is equal to their observed score, y sub I, minus their predicted score, y hat sub I. Now, as we add more and more predictor variables to our multiple regression model, the size of these residuals gets smaller and smaller. And to see that, let's go through a different hypothetical example. Now, before we begin, 2 points I want to make. First, I've made up this data so that it more clearly illustrates the point I want to convey. And second, this isn't exactly entirely correct in how we're looking at multiple regression. Now, I'll explain why at the end, okay? For this example, we have 25 adolescents, and our outcome variable is their ratings on an adolescent problem behavior checklist, where higher scores indicate that they're reporting higher levels of behavior problems. Our predictors are parent support, with higher scores indicating more support, and peer behavior problems, with higher scores indicating a youth is associating with friends who show more behavior problems. We'll start by only including parent support as a predictor. Now, here's a scatter plot predicting adolescent problem behavior, our outcome, based on the level of parental support, with the regression line drawn in as well. We see that the behavior scores range from 2 all the way up to 20, but there's clearly a negative relationship with the behavior scores getting lower as parental support values get higher. Now, this is important. The regression line tells us the behavior problem score that we would predict or expect to see for a specific child based on their individual, their specific level of parental support. But not surprisingly, some kids have higher scores than we would expect, more behavior problems than we think they should have given their level of parental support. And these cases are seen in the positive residuals. And other kids have lower levels than we would expect, lower scores, fewer behavior problems than we think they should have given their level of parental support. These cases have the negative residuals. Now, we're about to shift our focus to those residuals, and it can be easy to miss the implications of what this means. For example, let's look at one specific student, we'll call her Alex, who has a negative residual. That means she has a lower score, fewer behavior problems than we predicted given her level of parental support. In contrast, we have another student, Brian, who has a positive residual because his behavior problem score is higher than expected given his level of parental support. Now, in terms of residuals, Brian's residual is clearly greater than Alex's because his is positive and hers is negative. But notice that in terms of the actual behavior scores, Alex, even with her negative residual, has a larger score. Alex has more behavior problems than does Brian. Now, we're going to shift and start focusing again on these residuals. And as we do so, it's important to keep this in mind. Residuals aren't the same as the original raw scores. The values and what they may mean, and maybe even how the scores and individuals have appeared relative to each other, think Alex and Brian, has changed. To quote Dorothy,
Toto, I have a feeling we're not in Kansas anymore.
We're off to Oz. And with that, what about our second variable, peer behavior problems? We may wonder whether this is also related to adolescent behavior problems because it kind of makes sense, doesn't it? Hanging out with friends who have behavior problems may lead to behavior problems for you as well. So we go back and color code each of the points in our scatter plot in order to indicate the level of peer behavior problems for that student. And this is what we find. Now, clearly there's a trend. Notice that the kids with the largest positive residuals also had peers with the highest behavior problem scores. In other words, youth who had more behavior problems than expected, given their level of parental support, also associated with the most problematic peers. Similarly, the kids with the largest negative residuals had peers with the lowest behavior problem scores. In other words, youth who showed fewer behavior problems than expected, given their level of parental support, had friends with few behavior problems. This gets at one way of thinking about what we mean by statistical control or controlling for a variable. In this case, notice that we're not talking about kids having high or low levels of behavior problems. We're now factoring in a child's predicted score on the regression line and focusing on whether they're higher or lower than expected based on parental support. By controlling for parental support, we're in essence now focusing on those residuals in our model in which parental support was the predictor. So let's calculate the residual for each person and plot them. Now, if our assumptions were met, we should see something like this. If we don't, well, then there's things we need to do with our data or our model in order to ensure that we end up with the right regression equation in the end. More on that in future videos. Notice that our x-axis is the same. We're still looking at scores across the range of parent support. But notice the y-axis has changed. It's no longer adolescent problem behavior scores. Now we're talking about residuals after controlling for parent support. As a result, the scaling is also fundamentally changed. Remember, the original behavior scores went from 2 all the way up to 20, a range of 18 points. But the residuals only go from negative 4.9 up to positive 4.7. That's only 9.6 points. This reflects the reduction in the variance in our outcome due to our regression model. You can see it right here. Plus, notice the mean of the residuals is 0, and the residual of 0 indicates that a person's observed score was exactly equal to their predicted score. Now, notice that there's no association between parent support and the residuals for behavior problems controlling for parent support. The values for the residuals are pretty much the same across the entire range of parent support. This illustrates how we can statistically remove the effect of parent support from our behavior problem scores. Pretty cool, huh? Now, let's color code the residuals based on peer problem behavior. As we already saw, right, the largest positive residuals had larger peer behavior scores, and the largest negative residuals had the lowest peer behavior scores. We'll now perform a new regression analysis with peer behavior as our predictor. But instead of using the original adolescent problem behavior scores, we'll use the residuals we calculated after controlling for parent support. Let's look at the results for that analysis. Now, here's a plot of the residuals of behavior problems after controlling for parent support based on peer behavior scores. Notice the change in the x-axis, right? It's peer behavior. As we can see, there's a strong positive association. Now, this is no surprise, right? We've been talking about that already. Also, you can see that our new regression line is plotted in which we're predicting the residuals from our previous analysis, now based on peer problem behavior. And just like any regression line, we can calculate new residuals for this line. Let's take a look at those residuals. First, notice the change in the y-axis. These are now residuals controlling for both parental support and peer problem behavior. As with our first set of residuals based only on parental support, they're centered on 0. But notice that the range is even smaller now. These residuals go from negative 1.1 up to a positive 0.8. To see this, let's quickly jump back for a moment to the residuals based only on parental support. See, the residuals were much larger when we only controlled for parent support. By adding problem behavior, peer problem behavior, the residuals have gotten smaller and smaller. By adding variables, we're able to make predictions that aren't perfect, but on average, they're getting closer and closer and closer to the truth, closer to those observed scores. But remember that as we do this, as we add predictors in multiple regression, we're looking at their effect on residuals of our outcome variable after controlling for all of the other variables in our model. We're not simply looking at the original outcome anymore. Now, this example can be helpful, but as I said, it's not 100% correct. The problem is that it sounds like when you perform a multiple regression, the effect of one variable is calculated and then those results are set in stone. And based on that, the effect of another variable is calculated and then those results are set in stone. And that keeps going on as you add more and more variables to your model. But that's not how it works. when calculating your effects and regression coefficients in multiple regression, all of the predictor variables in the model are examined simultaneously, and all of those effects are recalculated each time a new variable is added to the model. The effect for each variable is estimated after controlling for all of the other variables in your model. Also remember, as I noted earlier, the residuals don't necessarily look as clean and consistent as seen in this hypothetical illustration. Later we'll talk more about what to look for with your residuals and adjustments that you may need to make to your variables or to the model in order to get the right results. And finally, another limitation of this illustration is that it implies that as we add more predictors, our multiple regression equation is still based on a line. But that's not how it works either. We're not dealing with lines anymore. We'll discuss that in our next video. Okay? Bye for now.